All right. Assalamu alaikum, everyone. I hope you are all having an amazing day so far. My name is Rafah Chahine. I'm a third year medical student. Inshallah, today I'm going to be explaining fatty acid oxidation. Just before we begin, here's my contact information in case you have any questions or concerns. Yeah, let's get started. So these are the doctor's objectives. And honestly, back in first year, the doctor's objectives are basically what made me not like it. But once I broke down the topic, it became my favorite, and I decided to do the same today. So I made my own objectives. So now I know it looks like a lot, but actually it's pretty simple. I just mentioned absolutely everything that is in the slides and I broke it down just for it to be a little bit more comprehensive. And we are going to be using this slide as a checklist and a checkpoint. So inshallah, it will be easy. Okay. So first of all, before we begin, I just want to make sure that we all have a proper foundation as to what we need to know before we go into all the nitty gritty of everything. So first of all, the body is a major source of stored energy, and adipocytes, which are the fat cells, they store our fats mainly as triglycerides, and that makes up approximately 90% of their cytoplasm. And after we ingest any meal, whether it be fatty or whatever, any fats that we take in are going to go to the small intestine and get packaged as chylomicrons. Now, when we get these chylomicrons, obviously they contain about 85 to 90% triglycerides. They're considered to be the biggest lipoproteins that we have in our body. From those chylomicrons, that's where we get the fatty acids that we need in order to proceed. Now, what happens to the fatty acids is beta oxidation, which is the main objective of today's lecture. And after beta oxidation, we get this acetyl-CoA. Now, acetyl-CoA has a bunch of functions, but the ones that we are most concerned about in the context of this lecture is the fact that it goes through the citric acid cycle and produces CO2 and H2O over here. 1 second. Okay, I think, okay. And so then fatty acid is a major fuel source during prolonged exercise and fasting. So during Ramadan, when glucose storage is out, we refer to fats in order to get the energy that we need. Okay, so now we mentioned triglycerides, but what exactly are triglycerides? So triglycerides are a form of fat that basically contain one glycerol on this side and 3 fatty acids attached to it. And just to explain a little bit about the structure, we have 3 different carbons that we're going to be referring to as C1, C2, and C3. Okay, now we are going to see exactly what happens to these fatty acids, which is oxidation, but what happens to glycerol, which we have a whole slide about, is also very, very important. So glycerol itself is an important molecule that helps the body and the liver specifically in processes such as gluconeogenesis and glycolysis. Okay, and then after the triglycerides are taken out of the chylomicron, they're going to go to the liver, muscle, and the heart for energy. And any triglycerides that might remain in the bloodstream are going to be transported to the liver and get repackaged as VLDLs. And we're going to see that happening when we talk about lipoproteins in general. Okay, so over here, this is where you're going to see the chylomicrons and the triglycerides get repackaged as VLDLs. But to break this down for you, honestly, I hate this diagram. Ever since first year, I just didn't get it. But alhamdulillah, I got it now and I can explain it to you. So firstly, let's just start from here. We ingest something, right? Dietary fat and cholesterol will go to the small intestine. And we said that they're going to be packaged as chylomicrons in the small intestine. So we get these chylomicrons. Now they're going to go into the capillaries. Okay, and in these capillaries, we have a very important process that's going to happen that we are going to talk about in detail, where these chylomicrons are going to be broken down by this enzyme called lipoprotein lipase. Now, after they're broken down, any remnants of these chylomicrons and the cholesterol are going to go to the liver and get repackaged as VLDLs, as we see over here. And then these VLDLs, because they also contain triglycerides, we're trying to get everything that we can. They're going to also get hydrolyzed by the same enzyme called lipoprotein lipase in the capillaries. And then we're going to get these intermediate density lipoproteins. And then we're going to get these LDLs from those intermediate density lipoproteins also through lipoprotein lipase. And then these LDLs, I'm pretty sure you have a whole lecture about lipoproteins, but just to give you like the rundown of what happens is that they are taken up by peripheral tissues like muscles and other organs by the LDL receptors, and their cholesterol, the cholesterol component of these low density lipoproteins, is used in order to do important functions such as the synthesis of steroid hormones and to make up the membranes of the cells in our body, the phospholipid bilayer and all that. And then after we use the cholesterol from the LDLs, they become high density lipoproteins, and then the whole process goes on and on and on. But we're not going into the details of lipoproteins because that's not the objective for today, but it's just a very simple rundown. Okay, now we want to put these triglycerides to good use. How do we even start to do that? First of all, I don't have the triglycerides, so I need to get them from the adipocytes or the chylomicron, right? So we're going to hydrolyze these triglycerides into fatty acids and glycerol. And then we're going to transport them to the tissues, whether it be the liver, muscle, or heart. And then these fatty acids, in order for them to actually begin beta oxidation, they need to go to the mitochondria, right? But in order for them to actually reach the mitochondria, we need to activate them. They can't just enter, go into the mitochondria and they begin beta oxidation. No, there's a process before that, and that process is activation. So we need to activate them, and then they can go into the mitochondria. In the mitochondria, that's where we start actual beta oxidation. So they're oxidized into acetyl-CoA, but then acetyl-CoA, citric acid cycle, whatever. So this is the entire rundown. Are we good? Well, I can't see the chat, but I'm assuming that we're good. Okay. So we're done with the first objective. We're going to move on to the second objective, and this is where we start step 1 of the initiation of beta oxidation or fatty acid oxidation. Okay, so first of all, I've been talking about triglycerides and this is what's going to happen, but we haven't even actually gotten the triglycerides yet. Now, in order to get them, you can look at this as though we have 2 different places we can get triglycerides. I'm referring to the chylomicron and stored fat. Chylomicron meaning the fat that we just ingested, and stored fat, the fat that we have under our skin. Okay, so starting off with the chylomicron. If you remember in the lipoprotein slide, I mentioned lipoprotein lipase. Now, this is where it comes into play, right? I told you in the capillaries, lipoprotein lipase is going to break down this chylomicron and give us triglycerides. Now, in order for that to happen, chylomicron is actually a pretty big molecule. So it needs to be anchored to the endothelial cell in my capillary. It gets anchored by lipoprotein lipase, which we see over here, this purple structure, this purple enzyme, that's lipoprotein lipase. This lipoprotein lipase can't just take it, it's not just attached to the endothelial cell. No, it is actually also anchored by something else that's very important that you need to know, which is this glycosaminoglycan called heparan sulfate. Okay, so recap of everything I just said. Chylomicrons are going to be in my capillaries. I need to get the triglycerides out of them. I'm going to use this very important enzyme called lipoprotein lipase, which is anchored to the endothelial cell by heparan sulfate, which is a very important glycosaminoglycan. Okay, and in this diagram, it doesn't show you where heparan sulfate is, but just trust me, it was in your slide, you need to know. Okay. Now, in order for this lipoprotein lipase to actually begin the process of hydrolysis of this chylomicron to give me the triglycerides, it needs to be activated by this protein called ApoC2. ApoC2 is an apoprotein that gets synthesized in the liver and is presented to the chylomicrons, and it can also be present in VLDLs. So I know that sometimes, or not sometimes, all the time, lipoproteins contain their own apoproteins because they naturally have them. But sometimes, or in this case specifically, ApoC2 is one apoprotein or apolipoprotein that gets synthesized in the liver and is given to this chylomicron solely for the purpose of activating lipoprotein lipase in our context. Okay? Okay. And once lipoprotein lipase is activated by this ApoC2, which is this blue molecule, it begins the hydrolysis of chylomicrons, and then we get the triglycerides. Is everything clear? If anyone can unmute and say yes, that would be amazing because I can't see the chat. Okay, I'm going to assume it's clear. Okay, thank you. So now we're moving on to stored fat. We're done with getting the triglycerides from the chylomicron. That is one way, okay? But let's just say that I maybe don't have chylomicrons. How do I get the triglycerides from the stored fat? So the way to do this is actually very interesting, and I really like this because it's very orderly. Now, in order to get triglycerides from my stored fat, I need these 3 enzymes, and they're called intracellular lipases. Now, we have three different types of intracellular lipases, which are adipose triglyceride lipase, or ATGL, hormone-sensitive lipase, or HSL, and monoglycerol lipase, or MGL. Okay? Now, the way things work here is that ATGL is going to break down this triglyceride, which has 3 fatty acids, into a diacylglycerol, which has 2. HSL, or hormone-sensitive lipase, is going to break down this diacylglycerol, which has 2 fatty acids, into a monosylglycerol, which has 1. And then finally, monoglycerol lipase is going to break down the monoglycerol, which has 1, into glycerol and fatty acids. So we're going in a stepwise fashion. Now, another important, which is this second bullet point, which is very, very important, is how specifically this entire reaction is activated with hormones. Now, we're specifically talking about HSL, and we're going to understand why HSL is the main character here, but it is activated by glucagon and epinephrine. So the reason that it's those specific hormones is because they are activated by hormones that our body releases when our body wants us to actually look for energy, when our body wants us to break down and use energy. Okay, so hormones like glucagon, epinephrine, norepinephrine, and adrenocortical hormone, the ACTH, those are the hormones that will activate hormone-sensitive lipase. And we're going to see how that happens in a later slide. But that also means that it is inhibited by some hormones, such as insulin. Now, it inhibits insulin because insulin is a hormone that our body secretes when it is telling us to store energy. So when insulin is on the rise, it's not like, okay, Allah, go and break down fat. No, it's telling us, hey, store fat, store this glucose, store everything that you've got, because we need to store that energy. So a little recap: to get triglycerides from stored fat, we need intracellular lipases. We have 3 of those. We have ATGL, HSL, and MGL, and they break down triglycerides in a stepwise fashion, going from 3, 2 to 1. And then HSL gets inactivated by hormones such as glucagon and epinephrine, and it gets inhibited by insulin. Now, this third bullet point is also important, which it might confuse you a little bit, but it's honestly pretty simple. Remember how I said the triglycerides are made up of the 3 carbons, the C1, C2, and C3? So going back to that, the order in which these carbons are broken down in the case of intracellular lipases is specific. So ATGL only likes to break down C1 or C3. HSL also only likes to break down C1 or C3, and MGL only likes C2. So the reason that this is important is because you have to come to the conclusion that, hey, C2 is always going to be the last carbon to get broken down in any case. So the order can be C1, C3, C2, or C3, C1, C2. Is that clear?
Yes, it is.
Okay, thank you. So now, after we're done with breaking down these triglycerides, we get free fatty acids and a glycerol, okay? Now, we are going to see exactly what happens to glycerol, but just to give you the baseline of everything, is that glycerol will go to the liver, and we said previously that it's going to help in processes such as glycolysis and gluconeogenesis, okay? In the case of fatty acids, they are actually going to be transported by albumin through the bloodstream until they reach the specific organs for beta oxidation. So now we get to this slide where we're going to talk about the intracellular mechanisms behind how all of this happens. Now, we're going to go step by step. So we have in this slide steps 1 to 6, and then we're going to move on to step 7 to 11. And I can repeat this as many times as you want me to, but we're going to start off simply with step number 1. Now, if you realize or notice, we have this hormone called glucagon, which I mentioned activates HSL. Before I said it activates HSL, I said, it activates this entire process. And this is the reason why I said that it activates this entire process, okay? So step number 1, we have a G protein coupled receptor, which I'm pretty sure you've already taken. And glucagon is going to bind to this receptor, activating it, which will cause this GS or G stimulant subunit to go and activate adenylyl cyclase. Okay, now in step number 2, adenylyl cyclase is going to convert ATP into cyclic AMP, and cyclic AMP is going to go and activate protein kinase A. Now, protein kinase A can do 2 things, which are step number 3 and step number 4. Protein kinase A in step number 3 will go and activate or phosphorylate hormone-sensitive lipase. This is why I said glucagon activates hormone-sensitive lipase, because it's the first thing that it phosphorylates. The whole process, that is the first thing that it phosphorylates. So pKa in step number 3 is going to go and phosphorylate HSL. In step number 4, it is going to go and phosphorylate this thing called perilipin. Now, perilipin is this protein that is actually associated or attached to CGI. Now, this is CGI, but this is also CGI. You don't really need to know this entire name. I just put it here for the sake of completion. I didn't even know this is what it stood for until 2 days ago. So that's besides the point. But pKa is going to phosphorylate perilipin. When perilipin gets phosphorylated, it no longer has the capacity to hold CGI. So in step number 5, CGI is like, you know what? I don't even need you, perilipin. I'm going to dissociate. It's going to leave perilipin behind, and it's going to go and activate ATGL, which is the first intracellular lipase that we talked about. Once ATGL is activated, it will begin the breakdown of triacylglycerol to diacylglycerol. Now, we're going to move on to step number 7. Now, in step number 7, we said, to break down from diacylglycerol to monosylglycerol, we need the hormone-sensitive lipase, which we have already activated with the help of protein kinase A. So this diacylglycerol will continue the breakdown with hormone-sensitive lipase, and monosylglycerol will continue breakdown with MGL, and we're finally going to get our 3 free fatty acids, which are going to go through the bloodstream and get transported with the help of serum albumin. And then in step number 10, it's going to go through a fatty acid transporter. And in step number 11, it will yield CO2 and ATP after the whole process of beta oxidation, citric acid cycle, and the respiratory chain, yada, yada, yada. So that's it. And this entire thing is a cyclic AMP mediated process. Obviously, we know that because it was all thanks to cyclic AMP activating protein kinase A. Is it clear, or do I need to repeat anything at all?
Can you just repeat the whole cycle quickly, please?
Okay, I got you. So in step number 1, okay, we have glucagon, which we said was one of the hormones that gets secreted when our body needs energy, right? So glucagon will go and activate this G protein coupled receptor. When we activate this G protein coupled receptor, it will let its GS or G stimulant subunit to go and activate adenylyl cyclase. Okay? Now, in step number 2, adenylyl cyclase is going to convert ATP into cyclic AMP, which is how we know this is a cyclic AMP mediated process. And this cyclic AMP will go and activate pKa or protein kinase A. Okay? Now, protein kinase A will do 2 things, which are step number 3 and step number 4. In step number 3, protein kinase A is going to phosphorylate or activate hormone-sensitive lipase. Okay? Now, in step number 4, it will go and phosphorylate perilipin. And we said, hey, perilipin is normally attached to or associated with CGI. But now that it is phosphorylated, it no longer has the capacity to hold CGI. So what CGI is going to do is in step 5, it will dissociate itself from perilipin, and it will go and activate ATGL. Now, once it activates ATGL, ATGL will now begin the process of breaking down triacylglycerol into a diacylglycerol. And then we move to step number 7, which is where the diacylglycerol will continue its breakdown with hormone-sensitive lipase, which we have previously phosphorylated, and go into monosylglycerol. And then that will be broken down by MGL to give me the 3 free fatty acids I was looking for. Once we have them, they're going to be transported through the bloodstream with the help of serum albumin, which is this blue structure over here. And then at step number 10, it will go through a fatty acid transporter into, for example, a myocyte or a muscle cell or any other cell. And then in step number 11, it will go through beta oxidation, citric acid cycle, and the respiratory chain to finally yield CO2 and ATP. Is there, do I need to repeat anything else, or is it clear?
Yep, it's clear. Thank you.
You're welcome. Okay. So now we're going to move on to glycerol. Now we're going to, because this entire lecture is dedicated to fatty acids, but we need to give some attention to glycerol, and this is its time to shine. This looks like it's complicated, but trust me, it's honestly very, very easy. Yes, you do need to know the names of the enzymes. I think, honestly, I'm not really sure. I think you need to confirm that with Dr. AJR, but I think you need to know them. But honestly, they're pretty easy. Inshallah, once I'm done explaining, it will be simple. Okay. So we're done breaking down the triglyceride. We got the one glycerol. Now, we said that the glycerol is going to go to the liver to give me intermediates that will help processes such as glycolysis and gluconeogenesis. Now, in order for me to do that, obviously glycerol itself is not going to do anything. It's not going to help me. I need to turn it into something else. This is where these 3 steps come in. Step number 1, okay, I want you to know this one thing about this enzyme, a kinase. Whenever I mention any enzyme about a kinase, it always means I'm going to use an ATP to phosphorylate. I'm taking a phosphate from the ATP and putting it somewhere. So even if it's not glycerol kinase, if it's X kinase, Y kinase, A, B, C kinase, whatever it is, if you ever hear a kinase, it always means I'm using an ATP to phosphorylate something. And this will help you a lot in the future when you don't really know what you're talking about. And then they mention a kinase and you're like, yeah, actually it's going to phosphorylate, you know? So it's like a nice thing to know, the way that names of the enzymes correlate with what they do. So glycerol is going to get converted into glycerol 3-phosphate with the help of glycerol kinase. What is the glycerol kinase going to do? It is going to phosphorylate glycerol using the help of ATP. So we added this phosphate. Now, if you're really interested in the tiny details, which is what I was like back in first year, I wanted to know what the element, what the 3 meant. So I'm just going to tell you what they are very easily, very simply. L over here, it means the hydroxyl is on the left side. This is called the Fisher naming system or something, Fisher, whatever. So the L here means that the hydroxyl is on the left side. Meanwhile, over here we see D, it means that the hydroxyl is on the right. You don't really need to know this, but just in case you want the whole picture. But the reason that it's called 3-phosphate is because this phosphate is on the 3rd carbon. That's why it's called glycerol 3-phosphate. So step number 1, glycerol is going to get converted into glycerol 3-phosphate with the help of glycerol kinase, which is going to use ATP to phosphorylate it. And obviously we're going to get an ADP in that process. And then in step number 2, we are going to use this glycerol phosphate dehydrogenase. Now, this is going to be relevant when we get to oxidation or beta oxidation, which is dehydrogenase. Whenever I'm using an enzyme that's dehydrogenase, I'm dehydrogenating something. I'm removing hydrogen from something. Biochemically speaking, hydrogen in our case is an electron, which means that we are performing an oxidation reaction. You know the oil rig system. Oxidation is loss of electrons. Rig or reduction is gain. So when I'm dehydrogenating something and taking hydrogens away from it, I am oxidizing it because it is losing electrons. So whenever you see a dehydrogenase enzyme, it always means I'm oxidizing. Okay, so now we get this glycerol 3-phosphate, and I'm going to use the help of glycerol phosphate dehydrogenase to oxidize it. I'm taking away the hydrogens, and I'm going to be reducing NAD into NADH and a free hydrogen. And then with that, we are going to get a dihydroxyacetone phosphate, which is otherwise known as a DHAP. Now, I'm pretty sure you took glycolysis and gluconeogenesis. You probably heard DHAP mentioned more than once, and it's a pretty famous term, and this is where we get it from, glycerol metabolism. Now, in step number 3, which is when DHAP becomes glyceraldehyde 3-phosphate or G3P, this term isomerization was not mentioned in your slide, but everything else was mentioned, so I decided, let's just mention it here in case you want to know. Isomerization is basically when I put dihydroxyacetone phosphate in a fitting room and it gets a makeover, and then it just becomes glyceraldehyde 3-phosphate. So basically, I'm not adding anything, I'm not taking anything away. We're basically changing the structure a little bit, and then it becomes glyceraldehyde 3-phosphate. So that's what happens with glycerol metabolism. I'm going to go through it one more time, and then we're going to see if we need to clarify anything else, okay? Okay, step number 1, we're using glycerol and glycerol kinase. Again, we said kinase, we're phosphorylating. So we're going to use ATP and add it, we're going to use the phosphate from ATP and add it to glycerol to give me glycerol 3-phosphate, and that is going to yield an ADP, obviously. Glycerol 3-phosphate, with the help of glycerol phosphate dehydrogenase, is going to reduce NAD into NADH plus a free hydrogen to give me dihydroxyacetone phosphate, or DHAP. DHAP is going to undergo this insane makeover, and it's going to be turned into glyceraldehyde 3-phosphate, or G3P. Is everything clear, or do I need to repeat anything?
That's clear.
Okay, perfect. So now, just a couple of things. The reverse of this reaction is how we produce glycerol for fatty acid synthesis. And these first 2 bullet points we already talked about previously. Okay. So this is a summary of everything that went in and everything that went out. So glycerol went in, ATP, we used it, NAD, we used it. What do we get? Dihydroxyacetone phosphate, the ADP after removing the phosphate from the ATP, and NADH after reducing NAD, plus the free hydrogen from the hydroxyl group that we took the hydrogen away. So this is the summary of the glycerol metabolism. Now, we're done with objective number 2. We're moving on to objective number 3. But before that, is there anything that I need to repeat or clarify before we move on? I'm assuming no. Okay. So we're moving on to objective 3. In objective 3, this is where we're going to start the major process of beginning beta oxidation, which is when we're going to talk about how we transport and activate these fatty acids. Now, I know this picture is insanely unclear, but hatta Google reverse image search couldn't even give me where this came from. Okay, I tried my best, but this is what we're getting. Now, what is in the orange box is what I'm mainly concerned about in this section. I'm mainly going to only be talking about the way it is activated and transported. Now, before we move on to the nitty-gritty details of everything, I want us just to understand what is going on in this picture specifically, because we're going to see it all happen under a microscope, okay? Now, the activation section of fatty acid activation is steps number 1 and 1 prime. That's it. That's all the activation is. It's just adenylation and acylation of coenzyme A. If I'm talking about transport, I'm referring to step number 2, 3, and 4. That's it. So let's break it down like that, okay? Adenylation, and acylation of coenzyme A together, and then transfer to carnitine, and reconjugation with CoA. That's all in transport, okay? So for now, all I want you to know is these 2 terms, and you need to know them for sure because it's going to make things a lot easier. Adenylation and acylation of coenzyme A. So these are for activation. Now, this is what happens in activation, and it looks like a lot. Okay, and it looks like a lot, but it's actually pretty simple. Now, if I ask you, what are the steps of fatty acid activation? I want you to answer and tell me it is adenylation and acylation of coenzyme A. But if I ask you, what is the meaning of fatty acid activation? You're going to tell me it is ATP-dependent acylation of coenzyme A. What does this sentence even mean? So just to break it down, adenylation is always ATP dependent. And you call something an adenylation reaction when it concerns ATP. So when I tell you it is ATP dependent, that is adenylation, and acylation of coenzyme A is acylation. Okay, fine. So how do we see this in action? We have this fatty acid over here, and we add this ATP to it and this coenzyme A. The addition of or acylation of coenzyme A to this fatty acid molecule is the whole point of activation. But I'm using ATP to help me because when I say adenylation, I mean, I'm covalently attaching an AMP molecule to them. That is the whole point of adenylation, okay? Now, if you go back, after everything that I've said, we have step number 1. I'm not going to say this word anymore. It's a tongue twister. It's making me tired. So step number 1, we have the fatty acid, and we're going to add ATP to it for the sole purpose of covalently attaching an AMP. That is adenylation. But in 1 prime, we have acylation, which is acylation of coenzyme A. So we're just adding coenzyme A to it. So that's basically what activation is. That's it. So now we're just going to continue with the details, okay? So we said we have this fatty acid. We want to add ATP to covalently attach AMP, which is adenylation, and then the coenzyme A for acylation. And then we get this entire thing, okay? But here's the problem. We get these 2 free phosphates because obviously, let's just say addition and subtraction. I have an ATP. I take away AMP from it. We're going to have 2 free phosphates. It's not going to have an adenosine. This adenosine is with the AMP that we just took. So it's going to have 2 free phosphates. Now, these 2 free phosphates are called pyrophosphates. And the reason that they're important is because of this second line over here. So phosphates is a very volatile molecule, okay? Which means that it gets hydrolyzed very, very quickly. When it gets hydrolyzed very quickly, it yields a very, very exergonic reaction. And we know what exergonic means. It means that we are releasing energy at a very insane rate, okay? And this is confirmed by this negative Gibbs free energy, whatever. So this is negative. This means that this reaction is highly exergonic. and it makes this entire reaction irreversible. Now, you're probably going to tell me, no, Rafah, I think you're actually wrong. It's not irreversible because there's a reverse sign over here, which I fully understand. But technically speaking, on a cellular level, this is not valid. Okay, because on a cellular level, the amount of energy that it used and expended is too much to actually get back. So the reversal of this entire reaction will take too much energy to actually go back. So it is considered to be irreversible. And yeah. Now this entire reaction is catalyzed by this very, very important enzyme that you need to know called LCAS, or long-chain fatty acyl-CoA synthetase. You need to know this entire name, but it's called LCAS, okay? So that's essentially what happens with fatty acid activation. Now, one thing that I want you to keep a note of for next upcoming slides is this last bullet point, which is the fatty acid acyl group recombines with coenzyme A for oxidation, and we're going to see that happen. It's not important right now, but it's going to be important later. But is a fatty acid activation clear?
Yes.
Okay. Okay, so we're moving on. Now, we're basically just re-emphasizing everything that we said. Adenylation is when we are using ATP to covalently attach an AMP molecule, and we see that happening over here. Now we move on to step 1', which is the acylation or adding coenzyme A, and then we're going to get this fatty acyl-CoA. This is an activated fatty acid. It is called a fatty acyl-CoA. Now, we're moving on to steps number 2 and 3. In steps number 2 and 3, we're going to use this thing called the carnitine shuttle, and then it can get transported into the mitochondrial membrane. But, so I said that LCAS, or long-chain fatty acyl-CoA synthetase, is a very important enzyme. The reason that it's important is because there are some people that might have a deficiency in this LCAS enzyme. And this disease is called adrenoleukodystrophy. So ALD, or adrenoleukodystrophy, is when this patient has a deficiency of the LCAS enzyme, and this will lead to the buildup of long-chain fatty acids in the brain and the adrenal cortex. Why long-chain fatty acids specifically? Because LCAS obviously is called long-chain fatty acyl-CoA synthetase, but also the process within which the medium chain and short chain fatty acids are oxidized is different, and we're going to see how different it is later on. But for adrenoleukodystrophy specifically, it's a deficiency of LCAS, buildup of long-chain fatty acids in the brain and the adrenal cortex. That's it. That's all you need to know about adrenoleukodystrophy. So now we're going to move on to the carnitine shuttle and the transport to the inner mitochondrial membrane. So now, this is the fatty acyl-CoA that we came to after activation. The problem is this CoA, it cannot attach to carnitine. Yani we can't take CoA and carnitine together at the same time into the mitochondria. So what we're going to do is that we are actually going to separate CoA for a while, and then we're going to get a fatty acyl carnitine instead of a fatty acyl CoA. So this entire process happens with the help of CPT1, or carnitine palmitoyl transferase 1, which is this red enzyme over here. It is on the external membrane of the mitochondria. So we get the acyl carnitine with the help of CPT1. After we get this acyl carnitine, now it will get transferred into the inner mitochondrial membrane with the help of this translocase enzyme. But now we need to bring back the acyl CoA. I want us to pause and take a second and go back to this last bullet point over here, where it says the fatty acid acyl group will recombine with coenzyme A for oxidation. This is what we mean by it will recombine. So momentarily, for a very short amount of time, the CoA will be separated from the fatty acyl because carnitine will take its place. And then once it's in the inner mitochondrial membrane after CPT1 and the translocase enzyme, it will recombine with it. That's what the last bullet point meant. But, so with the help of CPT2, we're going to recombine the acyl and the CoA. So now we have a fatty acyl CoA again, and this carnitine can now be reused. It will go through the translocase again to the cytosol, and it will wait for the next acyl CoA to show up. Okay, now malonyl CoA is a very important molecule that is produced during fatty acid synthesis. Hala, Rina, yesterday, my friend Rina, she gave a lecture about fatty acid synthesis, and you probably already know that malonyl CoA is produced as a result of that. So what I want to make clear to you is when we have fatty acid synthesis, why in the world would we have oxidation going on at the same time? Why would we be synthesizing them and breaking them down at the same time? So when we have malonyl-CoA in our bloodstream, in our body knows that, hey, we are currently synthesizing fatty acids. And so naturally speaking, this malonyl-CoA will try its very best to stop fatty acid oxidation. Now, malonyl-CoA, because we are currently undergoing fatty acid synthesis, it will go and tell CPT1, listen, I don't want you to work right now. We don't have the time for you. We are currently trying our best to synthesize fatty acids as much as possible. We don't want you here. So malonyl-CoA will stop CPT1. Now CPT1 is inhibited by malonyl-CoA. Is that clear so far? I'm assuming that is yes. Okay. Now, so we understand how the fatty acyl-CoA gets separated from CoA, and then it gets re-added to carnitine. And then now we get the acyl-carnitine, and this is done with the CPT1. Acyl-carnitine goes through the inner mitochondrial membrane through translocase, and then it gets recombined with acyl-CoA with the help of CPT2. Now, malonyl-CoA, which we know is a byproduct of fatty acid synthesis, will inhibit CPT1 because synthesis and oxidation cannot undergo at the same time. Now, the way malonyl-CoA is synthesized is that it is synthesized by acetyl-CoA carboxylase 2, which is an enzyme that you've probably taken in the fatty acid synthesis lecture. The reason that this is relevant to me is because the doctor mentioned in your transcription, and hey, it's called ACC2 because there's an ACC1, but the one that we're most concerned about is ACC2. And that's it for Journey to the Mitochondrial Matrix. Now, we're going to talk about the clinical significance of CPT1. So, patients can have CPT1 dysfunction in cases or in diseases such as type 2 diabetes and insulin resistance. Why? Because, as I previously mentioned, hormones like insulin, right, they want to store energy. They don't want to break down any fats for the use to get energy, right? So let's just imagine I have a patient that is type 2 diabetic. You have to understand that in type 2 diabetes, there's an early stage and a late stage, but the one that I'm most concerned about is the early stage. Because in type 2 diabetes, the body is currently undergoing insulin resistance, okay? Which means that it is not listening to insulin. So no matter what the body does, no matter what insulin does, it is just not going to listen to insulin. They don't like it, okay? So now the pancreas, what the pancreas is going to do is that it's going to go like, hey, the body's not listening to me. It's not listening to my friend insulin. What I'm going to do is I'm going to send out even more insulin in the hopes that the body will listen to me now. So that way, we're going to have hyperinsulinemia, okay? Now, hyperinsulinemia, or insulin in general, wants the body to store energy. So it's going to activate fatty acid synthesis. And we know from this slide that fatty acid synthesis yields malonyl-CoA, right? So when we have someone or a patient with hyperinsulinemia, that means they have an increased amount of fatty acid synthesis, which means an increased amount of malonyl-CoA, which will in turn inhibit CPT1. Now, this second bullet point is basically all about fatty acid synthesis. So when I have an increased amount of insulin, that means that I have an increased amount of fatty acids being synthesized, which will increase cytoplasmic fatty acid in skeletal muscles. And fatty acid oxidation will obviously be decreased because we are inhibiting CPT1 with malonyl-CoA. Now, on the other hand, we can have this other disease called a carnitine deficiency or a primary carnitine deficiency. So in the slide, we have two diseases. We said the dysfunction of CPT1, and now we have the carnitine deficiency. This carnitine deficiency is a genetic disorder that appears around the age of 5, and these patients can present with symptoms such as cardiomyopathy, skeletal muscle weakness, and hypoglycemia. Now, you need to know these symptoms because they might give you a case of like a 5-year-old child and they have symptoms similar or adjacent to what we just said, and you're going to have to diagnose them with a carnitine deficiency. But is everything in this slide clear so far? Yes or no? I'm going to assume that it is clear. Okay, thank you. So now we're moving on to CPT2. So we talked about the clinical significance of CPT1 and how the dysfunction is very prevalent in diseases such as type 2 diabetes and insulin resistance. And we talked about this primary carnitine deficiency, but we haven't talked about CPT2. So now we want to understand that CPT2 is in the inner mitochondrial membrane, right? We said that its main function is to recombine the the fatty acyl to its CoA. So we're bringing back the fatty acyl CoA and we're going to separate it from carnitine. Now the problem is when we have a dysfunction of CPT2, we are no longer able to re-add the CoA. This problem, right, can happen absolutely anywhere in the body, but the most common is a myopathy, or specifically it happens in the muscles, okay? And obviously this is a genetic disorder, so it's going to be autosomal recessive and it has a late onset. These symptoms, I'm not necessarily going to go through them, like it's just muscle aches, rhabdomyolysis. Rhabdomyolysis is when you have breakdown of the muscle. When the muscle gets broken down, it basically releases myoglobin in the urine, and that will lead to red urine and things like that. And these other symptoms you can read on your own. But yeah, so CPT2, it's in the inner mitochondrial membrane. Its main function is to re-add CoA to the fatty acid, to the activated fatty acid. But in this case, it will not be able to do that, so we cannot undergo beta oxidation. So all these tissues mainly contain CPT2, but the most common deficiency is going to occur in the muscles, and this is called a myopathy. And it is autosomal recessive and it has a late onset. Patients can present with muscle aches, rhabdomyolysis, episodes that are provoked by exercise and fasting, cold, or stress. And the symptoms can be exacerbated by high-fat, low-carbohydrate diets because obviously they cannot break down the fats. And muscle biopsy will show elevated triglycerides because we are not being able to break it down, these triglycerides, to begin with, because we cannot properly begin beta oxidation. And the primary treatment is to stop any muscle activity and just give glucose as their primary source of energy. Okay, so now we're done with objective number 3. Now we're moving on to the major objectives, which are objective number 4 and 5 when we move on to ketogenesis. But in objective number 4, this is where we're going to begin fatty acid oxidation. We're going to understand the prevalence of medium chain fatty acids, the role of the peroxisome, and how do we break down odd chain fatty acid as well. So before we move on, is everything that I've said so far clear?
Yes.
Okay. Now we're moving on to fatty acid oxidation. We're done with the orange boxes. We've talked about how it's activated with adenylation and acylation. We talked about the carnitine shuttle. We talked about the reconjugation with coenzyme A. Now we're going to move on to what happens inside the mitochondria, okay? Which is this green box. Now, before we begin, I want to note a few things down before we go into the nitty-gritty of beta oxidation. So first of all, the whole process of beta oxidation happens more than once. The reason that is because in beta oxidation, the whole point is to break down the fatty acid completely, which means that I'm trying to rid it of all of its carbons. But the problem is with beta oxidation, every one cycle of beta oxidation, the fatty acid only loses 2 carbons. So let's just say I have a long chain fatty acid, and that long chain fatty acid has 16 carbons. Obviously, after one round of beta oxidation, it will only have 14 left, which they all need to disappear before it is completely broken down. So beta oxidation is going to happen about 7 more times in order for that fatty acid to be completely broken down. Okay, then the names of the enzymes that we're going to talk about in beta oxidation correlate with what reaction they catalyze. And we already kind of touched upon this back during glycerol metabolism, because I told you in a kinase, we're using ATP to phosphorylate a dehydrogenase for oxidizing. So the best way to understand beta oxidation, in my opinion, is to understand how each enzyme works, okay? And then the last point is about the breakdown of short chain and medium chain fatty acids and how it is different, and we're going to see exactly how that happens later on. Okay, so now we're moving on to beta oxidation, and I'm going to switch to my files app in order to do that more properly. But before I begin explaining, I want to make sure, and I want to make it very, very clear that the doctor did say that the only enzyme that you need to know is acyl-CoA dehydrogenase, okay? But back when I was in first year, I found it to be so much easier for me to understand this entire reaction if I knew the names of the other enzymes, which is not a requirement, but it might help you understand the process rather than memorize it, okay? And before we begin, just a very little warning. I will be over-explaining a couple of things, a couple of like chemistry things, which are also not required of you, but they might help you understand the concept and why everything is called what it is, so much more. Okay? Fine. So I want to begin by explaining what's the structure of this fatty acyl-CoA is. So in this fatty acyl-CoA, I'm mainly concerned about these three carbons. So we have carbon number 1, carbon number 2, and carbon number 3. But the thing is, this one is called carbon number 1, but this one is called alpha, and this one's called beta. The reason that they're called that is because of their relation to this number 1 carbon. This is called a carbonyl carbon. Okay, so the reason that this is called alpha and the reason that this is called beta is fully related to their position in comparison to this carbonyl carbon. So anything after this carbon number 1 or the carbonyl is called alpha, which is carbon number 2, and carbon number 3 after that is going to be called beta carbon. Okay, so that is the primary thing that I want you to know about the fatty acyl-CoA structure. Okay, now we're moving on to reaction number 1. In reaction number 1, we are going to be using this enzyme called acyl-CoA dehydrogenase, and this is a family of enzymes. So it is multiple enzymes that work together to make this oxidation. Now, why is it an oxidation reaction? Because I previously mentioned in glycerol metabolism, any dehydrogenase enzyme will catalyze an oxidation reaction. Why? Because we are taking hydrogens away from the molecule, which means that we are taking electrons away, which is oxidation. So I'm using acyl-CoA dehydrogenase to oxidize fatty acyl-CoA. Now, when I oxidize fatty acyl-CoA, I'm removing hydrogens. But where am I removing them from specifically? I'm removing them from the alpha and the beta carbons. So I'm going to take these out. Okay, and this is why we get the CH instead of the CH2. But the thing is, I take out these carbons, where are they going to go? Yani, they can't just be free in the blood. That's it, we're done. No, they're going to go and they are going to reduce FAD into FADH2. So we're done with two things about reaction number 1. We're done with the removal of the hydrogens from the alpha and the beta carbons, and we're done with the reduction of FAD to FADH2. But now, before we move on, I want to make sure that everything that I've said so far is clear and not confusing, because when we get to part 2, it's going to get a little bit more chemical. Is everything good? Yes or no?
Could you re-explain just the portion that we need to know about the enzymes?
Okay. So acyl-CoA dehydrogenase is technically the only enzyme that you need to know. And this acyl-CoA dehydrogenase is very important because it catalyzes the first reaction of beta oxidation, which is oxidation. When we are oxidizing something, we are removing hydrogens. So I am removing the hydrogens specifically from the alpha and the beta carbons over here, and I'm giving them to FAD, which will reduce it to FADH2. So that's it for the first couple of things about the first reaction. But for the second reaction, which is the formation of a trans carbon-carbon bond. And I know it's a little bit confusing and it might be a little bit unnecessary, but you need to know what happens in each step. Now, in order for you to know what a trans carbon-carbon bond is, I'm going to explain to you what it is. So we can have a normal carbon-carbon bond, which is called a cis carbon-carbon bond, but we can also have a trans carbon-carbon bond. What that is two double bonded carbons that have their constituents on opposite sides. So let's just say that this is a hydrogen and this is like a variable compound. On the other side, in order for it to be a trans carbon, they need to be switched. So this is what makes a trans carbon. So where is the trans carbon in this entire picture? This is the trans carbon that I'm referring to. And you can't see this entire formation over here because this is a different, it's just, they're presenting the molecule in a completely different way. But is everything clear about the trans carbon-carbon bond and FAD and the alpha and the beta carbon?
Yes.
Okay, so now we're moving on to step number 2. Before we move on to step number 2, just a tiny little thing is now I want you to know this trans 2-enoyl-CoA. The reason that it's called trans 2-enoyl-CoA is, first of all, it's called trans because we have this trans carbon-carbon bond over here. The reason that it's called 2 is because this carbon-carbon bond is between carbon 2 and carbon 3. And enoyl, because we have an enol group. Now, what an enol group is when we have a carbonyl carbon like this. This is a carbonyl carbon, and it is bound to a double bonded carbon. This is what we call an enol group, okay? We see this happening in this entire section over here. All of this is an enol group. So this is why this end product of reaction number 1 is called trans-2-enoyl-CoA. Okay, so now that we know why this is called trans-2-enoyl-CoA, I'm pretty sure we can move on to the second reaction. Now in the second reaction, again, you don't need to know the enzyme, but it might be helpful when you want to understand this process. We have this thing called enoyl-CoA hydratase. Obviously, we have a trans-2-enoyl-CoA, so we're going to use an enol hydratase. From the name, it is a hydratase. So what am I doing? I am hydrating. I am adding water. When I add water, I am adding it specifically across this trans-carbon-carbon bond. When I add it across this trans-carbon-carbon bond, which is part number 1, I am going to form this hydroxyl group on the beta carbon, or carbon number 3. Okay? So that's essentially everything that happens in reaction number 2. So I'm going to repeat everything about reaction number 1 and reaction number 2 before we move on to 3. So in reaction number 1, we used an acyl-CoA dehydrogenase to oxidize fatty acyl-CoA. What did I oxidize and where did I remove the hydrogens from? I removed them from the alpha and the beta carbons, which are these two. Now, when I remove them from the alpha and the beta carbons, I'm going to use these hydrogens specifically to reduce FAD to FADH2. So we're done with this part and this part. Now, the third thing that it does is that it forms a trans-carbon-carbon bond. What this means is that we have these two carbons that are double bonded to each other, but what makes them trans is that their constituents are flipped. So it will be like this. So this is what finally makes the trans-2-enoyl-CoA. Trans because of this trans carbon that we have over here. 2 because it's in between carbon 2 and carbon number 3. Enoyl because this entire thing is an enol group. And again, what an enol group is when we have a carbonyl carbon that is bound to 2 double bonded carbons. This is an enol group. So this is what makes trans-2-enoyl-CoA. Now, in reaction number 2, we have an enoyl-CoA, trans-2-enoyl-CoA. We're going to use an enoyl-CoA hydratase, which will hydrate. From the name of the enzyme, we are going to be adding water. We are going to be adding water across this trans-carbon-carbon bond. Now, when we add water across this bond, we are going to form a hydroxyl group on the beta carbon, which we know is the third carbon, or 3. So this is what happens in reaction number 2. What is it going to yield? It is going to yield 3-hydroxy-acyl-CoA. 3, because obviously the hydroxyl group, which is the hydroxy, is on the third or the beta carbon. Acyl-CoA because this is an acyl-CoA. So this is what we're going to have at the end of reaction number 2. Now, to start off reaction number 3, I haven't fact checked this, but I'm pretty sure reaction number 3 is why this is called a beta oxidation, because we are oxidizing what is on the beta carbon, okay? So in order to do that, we are going to use this enzyme called 3-hydroxy-acyl-CoA dehydrogenase. Again, this is an oxidation reaction, a second oxidation reaction. So we are going to use a dehydrogenase enzyme. Now, what specifically are we oxidizing? We are going to be oxidizing the hydroxyl group and the hydrogen that is with the beta carbon right now. And again, when we oxidize something, we need to reduce something else, right? In this case, it is not going to be FAD, it is going to be NAD. So we're going to reduce that from NAD to NADH plus a free hydrogen, because we broke down to what? It's only going to take 1. Okay, now, the third thing that this third reaction does is forms a keto group on the beta carbon. Now, this is the last group that I'm going to be explaining, but what a keto group is essentially this part, this entire thing. This is called a keto group. Why? A keto group is when we have a carbonyl carbon that is bound to 2 carbons on either side. This is called a keto group. In the simplest form ever, this is a keto group. And this is what we see over here. So after reaction 3, what it gives me is 3-keto-acyl-CoA. Why is it 3? Because the keto group is mainly surrounded by or on the beta or the third carbon. Keto because it's a keto group. Acyl-CoA because it's an acyl-CoA. Is reaction number 3 clear?
Clear.
Okay. Thank God. Okay. So now we're moving on to the last and final reaction, which is pretty much the easiest. Now we have this 3-keto-acyl-CoA. We know why it's called that. We are going to be using this enzyme called beta-keto-acyl-CoA thiolase. So basically, what happened here is they got sick of the number 3 and they decided to call the third carbon beta now by its real name, right? So we're going to use this beta-keto-acyl-CoA thiolase to break down 3-keto-acyl-CoA. What do I mean by this? First of all, I told you need to what's it called? Understand the reaction from the enzyme name. What thiolase means, first of all, thiol is referring to the sulfur group that is usually associated with coenzyme A. Okay? So when I say thiolase, it means two things. First of all, I'm adding CoA, and second of all, I am breaking something down, right? So in reaction number 4, we have the 3-keto-acyl-CoA. We're going to use beta-keto-acyl-CoA thiolase to do two things. Number 1 is I'm going to break down the bonds in between alpha and beta carbon. The second thing I'm going to do is I'm going to add CoA. Why? Because right now, in this final step of beta oxidation, I am doing two things. I am trying to get a shorter fatty acyl-CoA, and I'm going to get an acetyl-CoA. Because as I previously mentioned, the whole point of beta oxidation is to get acetyl-CoA for it to go wherever it wants to go. But the second point is to take my fatty acyl-CoA and shorten it, 2 carbons shorter. So this is why we're adding a different CoA, because we only have one here. Acetyl-CoA obviously needs one, and then fatty acyl-CoA obviously needs one. So I'm putting another one, and this is where we get the thiolase from. Is everything clear?
Why do I need it to be shorter?
You need it to be shorter because the whole point of beta oxidation is that you are trying to break down fats, right? And when you break down fats, you produce acetyl-CoA. The point of breaking down fats is to get energy. Where do I get this energy from? From producing ATP, which occurs in the citric acid cycle, in the electron transport chain, all that kind of stuff. But in order for those citric acid cycle and electron transport chain to happen, I need a source of acetyl-CoA. These fatty acids are going to be my source of acetyl-CoA. With every beta oxidation, I get one acetyl-CoA. So the whole point is I need to break down my fatty acids to make them shorter to get an acetyl-CoA after each process. Does that answer your question?
Yes, thank you.
Okay. Now, does anyone want me to repeat everything that I said in a simplified form or no? I'm going to assume
If
that
you
is a
can go
no.
over it all, if you could go over it very quickly, that would be great.
Okay. So we're starting off with reaction number 1. We have a fatty acyl-CoA. We're going to use acyl-CoA dehydrogenase, which is the enzyme that you need to know. Okay, and from the name, we are oxidizing, right? When I oxidize, I'm going to remove the hydrogens from the alpha and the beta carbons over here, and I'm going to give them to FAD to reduce it to FADH2. Now, we're also going to form a trans carbon-carbon bond, which is what we see over here, and I previously explained what the trans carbon-carbon bond is. And what that is going to give me is a trans 2-enol-CoA. Then we're going to use this hydratase enzyme, which will add water or hydrate this molecule, and it will form a hydroxyl group on the beta carbon. Okay? We're done with step number 2 and 1. Now, in step number 3, we have the second oxidation reaction. So now we have the 3-hydroxy-acyl-CoA, 3-hydroxy because the hydroxyl group is on the beta carbon. Okay? And we are going to use this enzyme, the dehydrogenase, to oxidize it further. I am removing the hydrogen from this hydroxide, and I'm removing the hydrogen from this beta carbon, and I'm going to be reducing NAD to NADH with a free hydrogen. And then I'm going to form this keto group, as we can see over here, on the beta carbon. Now we get the 3-keto-acyl-CoA. The last thing that I need to do is get the acetyl-CoA, which is the whole point of this entire reaction. In order to do that, I am going to use this beta-keto-acyl-CoA thiolase. What this thiolase is going to do is that it will add coenzyme A, but also it will break down this bond in between the alpha and the beta carbons. Why? Because I am trying to make this original fatty acyl-CoA minus 2 carbons shorter. So I gave it 1 CoA and I made it 2 carbons shorter, and now I have an acetyl-CoA that can go to the citric acid cycle and the electron transport chain to yield ATP to give me energy. That is the whole process. So we started with oxidation, we had hydration, then a second oxidation, and then we cleave acetyl-CoA. Is it clear?
Clear.
Okay. Now we can go back to the slides. We're done with beta oxidation. This was basically the major point of this entire lecture. But now we are going to move on to this thing called MCAD deficiency. So what MCAD is it is an enzyme. It is called medium chain acyl-CoA dehydrogenase. Now, I want you to form these insane neuronal connections right now. And I want you to remember that this is called an acyl-CoA dehydrogenase. But this is called a medium chain acyl-CoA dehydrogenase. So this means that this enzyme is specific for the specific for medium chain fatty acid oxidation. So what does this mean? This entire thing was happening to long chain fatty acids. So this enzyme cannot actually break down medium chain fatty acids. It needs this medium chain acyl-CoA dehydrogenase, and it catalyzes the first step of medium chain fatty acid oxidation. But there is a problem. This enzyme can be deficient, okay? A deficiency in this enzyme, as we can all already assume, would impair the process of medium chain fatty acid oxidation or hydrolysis or breakdown, whatever you want to call it. So here's what's going to happen. Number one, the medium chain fatty acids are going to accumulate. But also number two is that we are not going to have the production of the acetyl-CoA that we've been wanting this entire time, right? Okay, so what's going to happen to these patients and how are they going to present? These patients might present with hypoglycemia and sudden death in the cases of no intervention. Pause. Why hypoglycemia? Our main source of energy when, for example, we are fasting or exercising is glucose. But in cases where we run out of glucose, I am going to look at fats. So these patients are going to have hypoglycemia because they've used up their glucose storages and now they want to look at fats and start breaking them down. But obviously they can't because they have an enzyme deficiency. So they might get sudden death. Now, this is often exacerbated by periods of vomiting or fasting. During the fasting, hypoglycemia would cause a profound lack of ATP for gluconeogenesis to take place. And the decreased amount of acetyl-CoA will lower this pyruvate carboxylase and limit ketogenesis. Pause. Pyruvate carboxylase is an enzyme that we will mention later on when we talk about ketogenesis. It's not important right now. So all I want you to know about the MCAD deficiency is MCAD stands for medium chain acyl-CoA dehydrogenase, and it is the enzyme that catalyzes the first reaction of beta oxidation of medium chain fatty acids. And so a deficiency in this enzyme would impair the breakdown of medium chain fatty acids and decrease the production of acetyl-CoA. How are these patients going to present? They're going to present with severe hypoglycemia and possible cases of sudden death if no intervention. These cases are mostly exacerbated or worsened by vomiting and fasting. Now, how or what are symptoms and signs of MCAD deficiency? You need to know these. First of all, we have a profound fasting hypoglycemia, and I already explained why. Now, we have low to absent ketones. This goes back to this last bullet point, which we will get to when ketogenesis comes around. But what you need to know for now is that we need acetyl-CoA for ketogenesis as well, right? So in order for ketogenesis to actually take place, the formation of ketone bodies to take place, we need acetyl-CoA. So in the case where we don't have acetyl-CoA, like an MCAD deficiency, these patients will have very low to absent ketones. So we're going to call this insane symptom combo hypoketotic hypoglycemia, okay? These patients can also have lethargy, coma, and death if untreated, and seizures due to neuroglycopenia, which is a lack of sugar or glucose for the brain, which is its main source of energy, and an increased amount of C8 to C10 acyl carnitines in the blood. Pause. What does C8 to C10 acyl carnitines mean? First of all, medium chain fatty acids, they have approximately 6 to 12 carbons minimum and maximum. These are what we categorize as medium chain. So when I tell you we have something that's 8 carbons and 10 carbons in length, we are assuming that it is a medium chain. And since it is not being broken down by beta oxidation, we're going to have an increased amount of their carnitines in the blood. So if we go back to the steps before that, the whole carnitine shuttle, whatever, we're going to have them combined with each other, and they're not going to undergo beta oxidation, which is why they're going to be increased in the blood. Okay, now these episodes we said previously will be provoked by an overnight fast, and in older children by illnesses such as the flu that might cause loss of appetite and vomiting. And finally, this one thing that was not mentioned in your slides, but will be or might be relevant, is hepatomegaly. Okay, I'll explain what steatotic liver is later on, but hepatomegaly is when the liver becomes enlarged. In the case of an MCAD deficiency, I told you that these patients will have a lack of beta oxidation of medium chain, right? Medium chain fatty acids are going to accumulate. The main place where they are going to accumulate is in the liver. This will make the liver much, much bigger, which is why these patients might present with hepatomegaly. The primary treatment of this disease is IV glucose, and to prevent any episodes of MCAD deficiency, you have to have frequent feeding because you don't want them to crave energy from their body so they don't go into this entire crisis. Very high carbohydrate and low fat diet because obviously they can't digest many fats. Okay, so now, before we move on, is MCAD deficiency clear? Okay, so now we're going to move on to a couple of cases. Do you have a question? Is there? Okay, so we're just going to move on to the cases. Now, these cases are from your slides, and we're going to take them in step by step, okay? So, we have a 5-year-old girl who has fatigue and difficulty walking. She walks normally at first, but becomes very weak and tired, and she has signs of mild motor delays, but is otherwise normal. Her vital signs are normal. Examination shows mildly decreased power in extremities, but no ataxia. Cardiac auscultation reveals an S3 gallop, and labs reveal hypoglycemia, elevated creatinine kinase, ketones that are absent in the urine, and the muscle biopsy shows very low carnitine content. Now, before we answer this question, I want to highlight what is important to me. First of all, she's a 5-year-old girl, so she's young. She has fatigue and difficulty walking, mild motor delays, and mildly decreased power in extremities. So she has a bunch of problems in her skeletal muscle, right? On cardiac occultation, this reveals an S3 gallop, and the labs reveal things like hypoglycemia, which is important for our lecture, ketones that are absent in the urine. This indicates a problem with oxidation, something along that process. We are unable to get acetyl-CoA. That's the whole point. And muscle biopsy shows very low carnitine content. Now, would anyone like to tell me what the answer is? If someone's answering in the chat, can someone read it out because I can't see it?
MCAD deficiency.
You're close. You're close. Okay, so this is not an MCAD deficiency. This is a primary carnitine deficiency. Now, the reason that this is a primary carnitine deficiency is, first of all, we said that these patients usually appear around the age of 5. This is a 5-year-old girl. I know this is very accurate or whatever, but this was from the slides. And these patients will present with symptoms of cardiomyopathy, skeletal muscle weakness, and hypoglycemia. So she has an S3 gallop, which is similar to what patients would present with if they had a cardiomyopathy, which for those of you that don't know what the cardiomyopathy is, you'll take it in more detail in 3rd year. She has multiple different symptoms of skeletal muscle weakness and hypoglycemia. The fact that ketones are absent in the urine means that there is a problem within the pathway and we're unable to get to acetyl-CoA. And the muscle biopsy shows very low carnitine content because it is a primary carnitine deficiency, and that should have been our main sign of what this disease is. But it is understandable why there would be some confusion. So, is this case clear?
Yes.
Okay, so now we're going to move on to case number 2. We have an 8-year-old boy who was brought to the ER with vomiting and lethargy. He was on a hiking trip with his family when they lost their food pack. The child became weak and was carried for the last mile, and he has not eaten in 24 hours. On examination, he appears very restless and he has mild hepatomegaly. The laboratory results are, this is hypoglycemia, acetoacetate or ketones are not detected. AST and ALT or liver function tests are pretty much normal, and the patient had seizures shortly after arriving at the ER. Now, let's highlight what is important to us specifically. First of all, he's an 8-year-old boy. He comes with vomiting and lethargy. He became weak and he has not eaten for the last 24 hours, which means he was fasting. And on examination, he was restless and there was mild hepatomegaly. We found hypoglycemia and no ketones detected, and this patient had seizures shortly after arriving at the ER. Would anyone like to make this diagnosis? Or no, not diagnosis. Which enzyme is most likely deficient in this patient? Which is the diagnosis, but
Is this one an MCAD deficiency?
yes, this one is an MCAD deficiency. So would you like to tell me why this one is an MCAD deficiency?
Okay, so you said it would get exacerbated with the fasting. It would have hypoglycemia and no ketones would be detected, as well as the hepatomegaly because of the steatotic liver.
Exactly. Okay. So this is an MCAD deficiency. This patient has hypoketotic hypoglycemia. He is weak and he has been vomiting and has been fasting. He hasn't eaten for the past 24 hours. He has mild hepatomegaly that is noted. This case is exactly why I mentioned hepatomegaly in the slide, although it wasn't in your lecture. And this patient has seizures shortly after arriving at the ER. And I said previously that the reason that he has seizures is because of neuroglycopenia or the lack of glucose in the brain to support the brain. And that's pretty much for these cases. Now we're going to move on to the other places where fatty acids can be broken down. Now, specifically, I'm referring to the peroxisome. Now, peroxisomes are an organelle that are found in cells. The reason that it is important to me to know why peroxisomes can break down fatty acids is because of the way that they do it. From the name peroxisome, we can correlate it with peroxide, right? So now, when long-chain fatty acids are broken down in the peroxisome, the acyl-CoA dehydrogenase, and if you remember, that is the first enzyme of beta oxidation, right? This acyl-CoA dehydrogenase, we said that it catalyzes an oxidation reaction where we basically remove the hydrogens from the fatty acyl-CoA, right? Instead of these hydrogens going to reduce FAD, like we've seen previously, it is going to be transferred to O2 or oxygen to yield H2O2, which is peroxide, okay? So instead of taking these electrons to FAD to produce FADH or to the electron transfer chain, whatever, it will go and give me peroxide. Now, in the peroxisome, we have a bunch of different enzymes that catalyze. They're called catalases, and they catalyze the dismutation of hydrogen peroxide into water and molecular oxygen. Basically, this is a bunch of nothing and everything at the same time. In the peroxisome, which is an organelle, the long-chain fatty acids can be broken down there using the acyl-CoA dehydrogenase enzyme that we mentioned as the first enzyme of beta oxidation. And we said that it is going to oxidize the fatty acyl-CoA and give me hydrogens, right? In the peroxisome, these hydrogens are not actually going to go and reduce FAD. They are going to go to oxygen. Why? Because they are trying to form peroxide. Once peroxide is formed, we have these catalase enzymes that are in the peroxisome that will catalyze the dismutation or the breakdown of hydrogen peroxide into water and molecular oxygen. That's all you need to know. There's nothing that's super relevant in this slide. But yeah. Okay. Now, before we move on to the next slide, this is an overview of fatty acids, okay? So far, we've been talking about long-chain fatty acids, which are basically 13 to 20 carbons long. I told you in the MCAD deficiency slide, usually medium-chain fatty acids are 6 to 12 carbons long. In these short-chain fatty acids, they are less than 6 carbons long. Now, the reason that this is relevant is because, for example, okay, in long-chain fatty acids, everything that happens to them is exactly as I said before. But in medium chain fatty acids, the difference here is they don't need a carnitine shuttle. They can diffuse through the mitochondrial membrane. They do need to be activated though, which is important, but they just don't need the carnitine shuttle. Same goes for short chain fatty acids. But the reason that I'm giving you this overview is because of this propionic acid pathway. Why is this important to me? Because let's just say, okay, whether it be long chain, medium chain, short chain fatty acid, if it is odd in number, right? So let's just say I had a C, okay, it says it right here. Let's just say if I had a C17, so a long chain fatty acid that was 17 carbons long. Basically, this propionic acid pathway tells me that if you had an odd number of carbons in your fatty acid, the beta oxidation will go completely normal until we reach the last 3 carbons. Why? Because these last 3 carbons are actually fatty acid on their own, and it's called propionate. As you can see over here, C3 is propionate, okay? So these are going to be called propionyl-CoA. And they are broken down completely differently to what the other fatty acids are broken, or how the other fatty acids are broken down. The way I'm going to break down these last 3 carbons of an odd chain fatty acid is using these 2 very important enzymes that you need to know. The first one is propionyl-CoA carboxylase, which will break down propionyl-CoA into methyl-malonyl-CoA. What you need to know about propionyl-CoA carboxylase is the cofactor that it needs, which is biotin. Biotin is vitamin B7. So we have propionyl-CoA. It will be converted into methyl-malonyl-CoA using propionyl-CoA carboxylase with the help of B7 or biotin. Methyl-malonyl-CoA will be converted into succinyl-CoA with the help of methyl-malonyl-CoA mutase that needs a cofactor B12 or vitamin B12, which is known as cobalamin. Okay, so recap, just a very short recap. Propionyl-CoA, with the help of propionyl-CoA carboxylase and vitamin B7 or biotin, it will be converted into methyl-malonyl-CoA. Methyl-malonyl-CoA mutase requires B12 or cobalamin as its cofactor to convert methyl-malonyl-CoA into succinyl-CoA. And then succinyl-CoA can enter the citric acid cycle chain to produce ATP. Is this clear? It's very easy, and if you are confused, I can repeat absolutely anything you want me to.
It's clear.
Okay, thank you. Okay, we're almost done. We are reaching the end. Now, the only things that we need to talk about are ketogenesis and how to use ketone bodies in our body for energy. So this is the easiest section. Now, I know this is like PTSD a little bit, but we're not going to be talking about all of this. Don't worry, okay? The reason that this is important to me is because I want to understand in what cases, okay, does acetyl-CoA go into ketogenesis? Because here's the thing. I told you previously that acetyl-CoA will typically go to the citric acid cycle to produce carbon dioxide and water, right? But in some cases, such as fasting, it will go to produce ketone bodies, which is the process of ketogenesis. Why is that? Because when we are fasting, okay, we have a decreased amount of oxaloacetates. So this means that acetyl-CoA cannot enter the citric acid cycle, because in order for acetyl-CoA to enter the citric acid cycle, as you can see, it needs oxaloacetates. So in the case of fasting, oxaloacetate is low. So acetyl-CoA cannot enter the citric acid cycle. So instead, it is going to go with pyruvate carboxylase, which, if you remember, I previously mentioned, into ketogenesis. That is all you need to know from this slide. Oxaloacetate is low because of fasting. Acetyl-CoA cannot enter citric acid cycle. It will go into ketogenesis. That's all you know. Now, we're going to move on to actual ketogenesis, which is actually pretty easy. Pretty easy. Now, in order to begin ketogenesis, we need 2 acetyl-CoAs. It is a requirement. Now, the reason that they put fatty acyl-CoA here is because they're basically telling you, hey, like you can get acetyl-CoA from these fatty acyl-CoAs with beta oxidation, but we already know that. We just finished beta oxidation. I'm pretty sure we are all aware of how fatty acyl-CoA works with ketogenesis and acetyl-CoA production. So let's just say I already have my acetyl-CoA. I want to start the process of ketogenesis. How? As 2 acetyl-CoAs are going to come together to form acetoacetyl-CoA with the help of thiolase. Okay? Now, 2 acetyl-CoAs with the help of thiolase, they're going to form acetoacetyl-CoA. Now, Acetoacetyl-CoA will undergo this rate-limiting step with the help of HMG-CoA synthase. Synthase, so we are synthesizing something, and in this case, we are synthesizing HMG-CoA synthase. HMG-CoA synthase is the rate-limiting enzyme in the rate-limiting step, okay? So what's going to happen is we are going to add a third acetyl-CoA with acetoacetyl-CoA to form HMG-CoA. So logically and technically speaking, this is basically 3 acetyl-CoA molecules together, okay? Mine is this one. This one is a CoA that got kicked out for some reason, but we can just summarize and say that this is 3 acetyl-CoA molecules together. So this is what makes up the rate-limiting step with the rate-limiting enzyme of ketogenesis. Tiny recap. 2 acetyl-CoAs will come together with the help of thiolase to make acetoacetyl-CoA. Acetoacetyl-CoA, with the help of HMG-CoA synthase, by adding another acetyl-CoA, will form HMG-CoA, which is 3-hydroxy-3-methyl-gluteryl-CoA, HMG-CoA. Just know HMG-CoA. Okay. Now, HMG-CoA is going to be cleaved by HMG-CoA lyase. Lyase, we are breaking something down, right? Lyase, we're cleaving it. So HMG-CoA, with the help of HMG-CoA lyase, is going to lose 1 acetyl-CoA and become acetoacetate. Okay, now, acetoacetate can do one of 2 things. Number 1 is that it can be oxidized, which means we are using a dehydrogenase enzyme. So it can be oxidized by 3-hydroxybutyrate dehydrogenase into 3-hydroxybutyrates. Yeah, okay, my bad. So acetoacetates, not oxidized, it's going to be reduced dehydrogenase. My bad. Okay. So acetoacetate is going to be reduced by NADH and its free hydrogen to give me 3-hydroxybutyrates. This is the first thing that can happen to acetoacetate. The second thing is very spontaneous. It can happen at any point. So acetoacetate can very spontaneously decarboxylate to form acetone, which is a volatile compound that is released in the breath. That's basically it for ketogenesis. Is it clear, or do I need to repeat anything?
What exactly do you mean by rate-limiting step?
So rate-limiting step is basically when it is any rate-limiting step is basically referring to when the reaction has, for example, like a point of no return. So when we undergo the rate-limiting step, خلاص, this is when the reaction is like you can't stop it from here on out and you can't go back. So it is a vital portion of any process that occurs. And because of that, we have a rate-limiting enzyme, which is in this case HMG-CoA synthase. And the rate-limiting step is the formation of HMG-CoA from acetoacetyl-CoA. Is there anything else that I need to clarify? You're welcome. Okay, so I'm assuming there's nothing else here. Now we're going to move on to ketolysis, or the use of ketone bodies in peripheral tissues. Now, we're basically going backwards from here. We formed these ketone bodies from 2 acetyl-CoAs into 3-hydroxybutyrate or acetone. Now we just want to go back, okay? So the reason that, okay, before I say anything, this is where synthesis of ketone bodies happens, in the liver. Now, in order for me to actually break them down, this cannot happen in the liver, and we're going to understand why in a bit. So we make the 3-hydroxybutyrates. It will go to, for example, the muscle cell. And in the muscle cell, this 3-hydroxybutyrate will be oxidized to give us acetoacetate. We saw here, it got reduced, right? We added hydrogens to it to give me 3-hydroxybutyrates. So now I'm going backwards. I'm going to oxidize it and reduce NADH or whatever, and then it's going to give me acetoacetate. Now, this is important. Acetoacetate will become acetoacetyl-CoA with the help of thiophorase. Thiophorase is a very, very important enzyme that helps acetoacetate alongside succinyl-CoA to turn it into acetoacetyl-CoA. So from 3-hydroxybutyrate, we oxidized it. We turned it into acetoacetate. acetoacetate to acetoacetyl-CoA, we are going to use succinyl-CoA and this very important enzyme called thiophorase. Then the acetoacetyl-CoA will become two acetyl-CoAs as we saw over here. That's basically ketolysis. Now, this reaction is obviously reversible in the case of ketogenesis. But a few other things that you need to know is why this reaction cannot happen in the liver is because in the liver, they actually lack this enzyme called thiophorase. We don't have thiophorase in the liver. So no matter how hard the liver tries, it will not be able to break down ketone bodies. That is why they need to go to peripheral tissues such as the muscle. But another tissue or organ that needs ketone bodies is the brain. Now, other than the muscle, the brain very, very efficiently oxidizes acetoacetate and 3-hydroxybutyrate to acetyl-CoA. The reason for that is because one of the main ways that the brain receives its energy in the case of fasting is through ketone bodies. So it needs to be efficient at this breakdown, and it efficiently oxidizes acetoacetate to and 3-hydroxybutyrate to acetoacetyl-CoA, then to acetyl-CoA. Is it clear so far?
Clear.
Okay. We are done with fatty acid oxidation and ketogenesis and all that. Thank you all for listening. I hope it helped and it made it easy. For my sake, please fill out this form if you have any feedback you want to give on this session. And I want you all to stay tuned for this next session that is going to be given by my friend Rafah Adwan, which is about cholesterol and steroid metabolism. And that's it. Thank you, everyone.
Thank you.
Thank you.